Alright, in this video we are going to go over section 7.6, which is finding volumes of a solid revolution using integrals. It's one of a lot of many fun applications of integration. So let's look at the bigger picture here, and so we can see what all this about. Alright, so I'm going to draw the graph of some function. Alright, I don't know, maybe any function f of x. Okay, this is f of x. So this is what we're going to do here. I'm going to rotate the graph about the x-axis. If we do that circularly, we are going to generate a solid. We're going to get a 3D image. Okay, so we're going to get something like this. So let me make some 3D effect. Okay, so it looks kind of a solid. All right, so that's what we're going to get. We are going to use integrals to find the solid of a revolution. Now, how do we get the formula? Because the formula is right below. You can see it here. However, let's justify it real quick. So we are going to look at the very basic case of finding volumes of solids of revolution called the disk method. So what do we know by the disk? What do we mean by the disk method? So I'm going to make a circle here. I'm going to make another there. And I'm going to take basically when I take this sample right here, it's going to become some sort of a disk. Alright, it's going to become like a disk, which I'm going to draw it here. Hopefully it's good enough to make it look like a 3D. So this disk has some thickness which is called delta x, and we know that the base of this cylinder, if you will, if you look at this cross-sectional, if you put your eye here, right, if you look at this solid, you're gonna look at this circle, but that circle has some thickness, right, and that thickness will be like the height of the cylinder. So volume of cylinders will be given by the area of the circle times the height of the cylinder. In this case, the area of the circle, we know the formula for that, which is pi r squared, and the height, which is the thickness of this cylinder, we call it delta x. Again, you might remember from the first semester calculus the intuitive definition, or let me rephrase this, the geometric interpretation of the integral, which gives us the area under the curve. So the thing is to make some rectangles as fine as possible in order to make an accurate area. So we're gonna have the same approach here. I'm gonna have another cylinder here, and more and more and more. If I add all these volumes, we add all the volumes, let's say total volume will be the volume of the solid Let me call it 1, volume 1. Let me call this volume 2. All right, let me use another color here. I'm going to use this kind of a green. Okay. Another disk here. That's volume 3. If we have infinitely many of this, we are going to get a more accurate volume of the solid. So we are going to have eventually the sum of all this pi r squared delta x. Okay. So in this case, let's call it x sub I, which is the ith disk, the ith volume. If we call a limit, we make, let me choose the right letter, from I equals to, let's say 1 to n, okay, with n being infinity, we are going to get, let me call this n. Call this n. That's going to give us the volume of the solid. But what about the r of x? In this case, this r of x will represent the function f of x. This is going to be our r, that's the radius of the solid. In other words, the limit n approaches infinity and I equals 1 and pi f of x squared delta x. If we evaluate the limit using Riemann sums, or as we have done in the previous semester, we get an approximation to, or a good approximation actually, which is going to be the integral. And ultimately that's what we're going to use. Alright, so let's do a couple of examples. So let's find the volume of the solid generating by revolving y equals x squared from 0 to 3 about the x-axis. So y equals x squared, that's the same as having a parabola. Okay, parabola. But in this case, we're going to rotate this about the x-axis. So the following solid is going to get generated. Some solid like this. We are going to get this solid. It's going to look like a Kisses chocolate if you look at this. So let's set up the problem. So v equals pi times the integral from a to b of f of x, quantity squared dx. So in this case, f of x is y equals x squared, quantity squared, so we square the function, don't forget about that squared, and the limits are going to go from 0 to 3. Alright, so let's simplify the integrand, 0 to 3, x to the 4th dx. Okay, and all we need to do is integrate using the general power rule, x to the 5th over 5 evaluated from 0 to 3. So all we do is upper minus lower that is 3 to the 5th power minus 0 to the 5th power. So 3 to the 5th power, that's going to give us a big number. That's 243. 243 minus 0 is just 143. That multiplies pi over 5. And in this case, I would just call it units, because this could be units cubed. This could be centimeters cubed, this could be inches cubed, or meters cubed. So it doesn't specify in the problem, but sometimes some applications might ask you to put the units. Let's do another example. So find the volume of the solid generated by revolving y equals 4 minus x squared about the x-axis. So in this case, the problem looks different because they're not giving us the limits of integration. However, if we observe if we observe the picture of this, so this is basically the same as saying y equals negative x squared plus 4, which is a parabola shifted 4 units up, and due to the negative in the front, in the leading term rather, the parabola is going to face upside down. All right. So, and also if we set this equal to 0, to find the x-intercept, we get plus or minus 2. So this parabola will have the following limits of integration. Negative 2, 1, 2, 3, 4. So we are going to have upside down parabola. Okay, and if we rotate this about, or revolve about the x-axis, we are going to have the following. So we're going to have, it's kind of an ellipse, not quite like an ellipse, but sort of. And well, to make it look like 3D, I'm going to make that to make it look like 3D. Alright, maybe darken the top and the bottom so it looks some sort of 3D. Alright, so that we're going to have basically like the volume of an egg. Okay, so let's find the limits of integration. So the limits of integration are going to go from x equals negative 2 to x equals positive 2. So the volume, the formula to find the volume here will be the following. The integral from, okay, pi times the integral from a to b, again, of f of x, quantity squared dx. Okay, so let's a negative 2 do positive 2, and this will be 4 minus x squared quantity squared dx. All right, I'm gonna show you a little trick here, right? So we don't spend too much time on computations. Okay, so because in this case it will become very annoying to plug in for 2 and for negative 2, and on top of that dealing with negative signs. So this is the trick right here. The trick is, if you look at this solid, well, my picture is not perfect, however it's perfectly symmetric. All right, so what we can do is find the limit from x equals 0 to x equals 2, and then whatever we get, multiply by 2 to get the other part as well. Because if we evaluate the lower limit at 0, that's going to simplify a lot of the calculations. So this trick can be done only when your region of integration is symmetric. So note, since the region of integration is symmetric, we can do this. We can do that. So this will be the integral, so pi times the integral from 0 to 2 of 4 minus x squared quantity squared dx, and multiply that by 2. Let's expand this binomial to pi times the integral from 0 to 2. This is going to be 4 squared, that's 16, minus 4 times x squared times 2, twice the product of both, that's 8x squared and then plus x to the fourth power dx. So all we do now is integrate this function. So that will be 2 pi times the integral of 16, which is 16x, the integral of negative 8x squared, which is 8/3 of x cubed, plus x to the fifth over 5, evaluated from 0 to 2. Okay. As usual, we do upper minus lower. So I'm going to do 2 pi times 16x, rather x, it's going to be the upper limit, minus 8/3 times the quantity 2 squared, rather cubed, plus 2 to the fifth over 5. So 2, 2, and 2. Now, for the rest of the calculation, what happens when you plug in the number 0 over here, here, and here? Everything is going to get zeroed out, right? So that's why we did the trick of taking advantage of the symmetry of the region of integration to avoid too many calculations, because if we didn't do that trick, we keep it the original way, we get a negative 2 over here, and we will have to evaluate another big chunk here, and that's what we want to avoid. We don't want to do many calculations. Nevertheless, if you want to do it the other way around, you might want to try. You should get the same answer, but otherwise, that's going to take forever to simplify. So let's keep simplifying this expression. I'm going to have 2 pi. I'm going to have 2 pi. 16 times 2, that's 32. Minus 2 to the third power is 8. Times 8 is 64. 64 thirds. And 2 to the fifth power is 32 fifths. So let's use a calculator for this. Okay. Let's see if I can use a calculator. So this will be 32 minus 64 over 3 plus 32 over 5. I'm going to do that, and I'm going to use the frac command because we want fractions, and that's going to be 256 over 15. So 2 pi times 256 over 15, which is the same as 512 over 15, 500 pi over 15. And that's final answer. So those were a couple of examples in which we find volumes of solid by integration. Now, let's do a very typical problem in which they ask us to use integrals to find the volume of a sphere. All right, let's recall the formula for the volume of a sphere. We know that the volume is 4/3 pi r cubed. We are going to get this formula using integration. All right, so how are we going to get a sphere? A sphere, if you think about it, it's no other than a solid generated by revolving a circle around, could be the y-axis, could be the x-axis, it doesn't matter, because the circle is, if centered at the origin, because that's our first assumption, the circle is going to be centered at the origin. So we are going to get, we can revolve it in any direction, and we are going to obtain a solid sphere. So let's see. Let's start with the equation of the circle. Which is given by x squared plus y squared equals r squared. Of course, there's the shifted version like x minus h squared plus y minus k squared, but it's not going to be the case. We are going to make this as simple as possible so the calculations do not get very weird. So I'm going to solve for y. So in this case, the thing is, when you take the square root of both sides, you are going to obtain y1 equals the negative r square root of r squared minus x squared, and y2 will be the positive r squared minus x squared. Okay, that's what we're going to obtain. So we are going to choose one. I'm going to choose the positive one because that's going to be the more convenient to work with. So I'm going to draw a picture here, and I will only use the upper part of the circle, the upper semicircle. So let me call this lower. Because of the negative, it's going to lie below. And this will be the upper semicircle. All right. Lower semicircle, upper semicircle. All right. And in this case, we know that the radius is r. So the distance from the origin to the endpoint is r, negative r and r. All right. So this will be y equals the square root of r squared minus x squared. Okay. And we are going to integrate that from negative r to r. Right, whatever that radius is. Could be radius 3, the unit circle, which is radius is 1, radius 8, or whatever number. So in this case, we're going to generalize this, and we are going to obtain this volume. All right, so the volume of a solid of revolution will be pi, as we did before, from A to B, f of x quantity squared dx. Okay, so let me continue over here. I'm going to continue here, and I'm going to start plugging in the information. I'm going to integrate from negative r to positive r for the function r squared minus x squared quantity squared. It's going to look ugly at the beginning, but look what's going to happen here. The squared cancels the radical. Okay, squares cancel the radical, and in this case, pi from negative r to positive r of r squared minus x squared dx. All right, again, in this case, I'm going to use the same trick with the symmetry, right? By symmetry, notice the symmetry of the semicircle. This is the same as integrating from x equals 0 to x equals r. So by symmetry, and then multiply by 2. So we get the following. This is going to be the integral from 0 of pi from 0 to r of r squared minus x squared dx, and multiply that by 2. All right. So in this case, all we do here is integrate using the general power rule. 2 pi times the integral of r squared with respect to x. This is just a number. This is going to be r squared x minus x cubed over 3, evaluated from 0 to r. I'm going to continue over here. I will indicate it with the arrow here. So I'm going to apply the fundamental theorem of calculus. Notice we integrated with respect x. So these numbers, the upper limit and the lower limit, are going to be plugged in the variable x, not r. r again should be treated as another constant. Okay, so this is going to be 2 pi times r squared minus 3. All right, plugging in the upper limit, this is r and this is r. Notice the lower limit, for the lower limit you can just say minus big 0, because what's going to happen if you plug in this 0 over here and there? Everything is going to get zeroed out. So now let's simplify everything we have here in terms of r. R squared times r, that's going to give us r cubed minus r cubed over 3. So this is basically subtracting 1/3 from 1, or 3/3. 3/3 minus 1/3, that's going to give us 2/3. 2 times 2, that's going to give us 4. The denominator is 3 pi r cubed. All right? Isn't it the same formula that we learned in geometry or basic algebra? And this is the end of the derivation. And also we call it the end of this section. I'll see you on the next video.